Let's consider ionic bonding in a little bit more detail. So let's take lithium and chlorine to form lithium chloride in a 1-to-1 Joseph-Proust definite proportion. If I look at the number of electrons inside lithium, I look at the atomic number, the Z number, and I can see it's 3. I look at the atomic number for chlorine, and I can see it's 17. To look in more detail why this forms, let's write the electronic configurations. So lithium has an electronic configuration of 1s2, 2s1. So it has 3 electrons total, 2 electrons in energy level 1 in an s orbital, 1 electron in energy level 2 in an s orbital. Chlorine has 17 electrons total. So if we write the electronic configuration for that, it would be 1s2, 2s2, 2p6, 3s2, 3p5. We have 17 electrons total, 2, 4, 10, 12, 17. And if we look at the valence electrons, because that's what's important in bonding, let's look at the valence electrons for both. So to find the valence electrons, you go to the highest energy level, or the valence shell, or the principal quantum number, the highest principal quantum number. So in this case, we're looking at energy levels. We have energy level 1 or 2. So clearly 2 is the highest number. And in that level, we have 1 electron. So lithium, although it has 3 electrons total, it's only got 1 valence electron. And that's exactly why lithium is in group 1. It's an alkali metal. If we now turn to chlorine, we have 3 is the highest energy level. And there are 2 of them because there are 2 sublevels. There's sublevel S and sublevel P, both at level 3. We have 2 electrons in the s orbital, 5 in the p orbital, both at level 3, so we have 7 total. So I've got 7 electrons total. Now, the rule of bonding with metals is metals have to lose their valence electrons. So lithium must lose 1 electron. This one exactly. The rule with nonmetals is they must fill the valence shell. Well, the valence shell is the highest energy shell. In this case, it's shell 3. And so, whereas the subshell S is full with 2 electrons, the subshell P can take a 6th electron. So that's perfect. You've got to lose 1, and I've got to gain 1. So if you must lose 1 and I must gain 1, let your electron loss be my gain. So there's only 1 electron involved here. The exact electron that lithium loses is the exact electron that chlorine gains. We've looked at this already in a previous video, and we've said that lithium with its Lewis dot and chlorine with its 7 dots, where each dot represents a valence electron, and it's 1 box. So we've looked at this already and said that the dot from lithium enters the box of chlorine. That leaves us with a positive charge on lithium. That leaves us with a net negative charge on chlorine because of the presence of that extra electron. And the ionic bond is the interaction of these charges. So that's one way to look at it. We're now going to introduce a slightly different way to look at this in terms of potential wells. So just like water will find the lowest point in a room and will fall down a hole, energy in general will always find the lowest level it can exist at, and it will fall down energy holes. So if we imagine we imagine lithium's electron is in a hole, these lines just represent shells. So for example, this could be shell 1, shell 2. So actually, let's put the electron in shell 2. So this line is just a shell. The details of this line for this video are not crucial. So let's imagine we have shell 2, and we only have one electron in shell 2. And this is the shell of lithium, or the well, the energy well of lithium. And the reason why lithium exists in the first place is because its electrons are trapped inside this well. They've fallen down into this potential well. So we'll call it a potential well. Now, chlorine also has a well. So let's say this is chlorine. Now, chlorine has 3 levels. Now, let's say chlorine's box is over here. So chlorine has an opening in its 3p subshell, which here we've drawn as this box that can accept the 6th electron. So I've got a well for lithium, and I've got a well for chlorine. Now the way I've drawn this, if I were to write energy here, or potential energy specifically, and then over here I would have time or reaction progress. So with the passage of time, I go from the left of the diagram to the right of the diagram. And I can imagine that the electron is now going to come out of here somehow, maybe through the collision energy as the chlorine and the lithium bump into each other. The mechanism is not relevant to this video, but somehow that electron is going to fall down a potential well. Notice that this box has a lower energy than that electron is currently. So this idea of energy flowing downhill, in being trapped in wells, I think this is a fruitful way to think. So this electron is now going to get stuck in here. And once it's in here, it would no sooner come out than water would come out of a sinkhole. You know, you can pump water out of a sinkhole, you can forcefully rip this electron out of chlorine, but it wouldn't naturally happen of its own volition. Something would have to happen to it. So because the electron is quite happily stuck in the potential well of chlorine and doesn't just come out of its own free will, we have a stable interaction. We have a stable Cl-, and therefore, by the fact that it can't regain its electron again, we have a stable Li+.